Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So today, I want to discuss about wear and surface treatment, long answer type questions. With answers we will discuss. So the topic is wear and surface treatment module 2. So long answer type questions. So in this, sometimes they will ask like this question, discuss the effects of the following parameters on wear rate. So what are the effects are there? So all these effects, all these parameters, effects on the wear rate. So one is load, temperature, surface films, compatibility, and crystal structure. So one by one, you have to discuss. So what is the load effect on wear rate? What is the temperature effect on the wear rate? So similarly, surface films, compatibility, crystal structure. So the wear rate of materials in tribological systems influenced by variety of parameters. So one is load. So what is this effect? The increase in load. So generally, an increase in load leads to higher wear rates. This is due to the greater force applied at the contact points, which can cause more significant deformation and material removal. So whenever increases the load, it leads to cause of higher wear rates. The mechanisms under high loads, mechanisms like adhesive wear, the wear material is transferred from one surface to another surface, and abrasive wear, where harder particles are asperities flow through a softer surface are more pronounced. So this is the mechanism. So under higher loads, the mechanisms like adhesive wear. So this all this leads to effect of wear. The threshold. So there is often a threshold load above which the wear rate increases dramatically, potentially leading to catastrophic wear or failure. So next, temperature. The effect is increased temperature. Elevated temperatures can both increase and decrease wear rates depending on the material and the operating conditions. So the elevated temperatures can affect on wear, increase or decrease. That is depends upon the operating condition. So similarly, material properties. High temperatures can soften materials, reducing their hardness and increasing wear. In some materials, however, higher temperatures can lead to oxidation, creating protective oxide layers that reduce wear. Thermal expansion. In thermal expansion, differential thermal expansion between contacting materials can increase wear due to changes in contact geometry and stresses. So lubrication, elevated temperatures can degrade lubricants, leading to increased friction and wear. So whenever the more temperature is present in between the contact surfaces, there the lubricant will be degraded and it leads to increase the friction. So whenever friction increases, then wear also automatically will increase. So in thermal expansion also same, the expansion between the contacting materials can increase wear. So we will due to the changes of temperature in between them. Next, surface films. So what is the effect of these surface films on wear rate? Protective films, surface films such as oxides, sulfates, or deposited coatings can significantly reduce wear by providing a protective barrier that prevents direct contact between the base material. The lubricant films reduce wear by decreasing friction and preventing metal to metal contact. So similarly, the film breakdown is if the surface film is not stable or wears away quickly, the underlying material may experience increased wear. Next term is compatibility. So what is the effect? The material compatibility of the materials in contact plays a crucial role in determining wear rates. So compatible materials with similar hardness and good bonding characteristics tend to have lower wear rates. The chemical compatibility. Chemical interactions between the materials can form beneficial or detrimental compounds. For example, some metal pairs can form low shear strength compounds that reduce wear, while others may lead to increased wear due to the chemical reactions. The adhesion and galling. So poor compatibility can lead to adhesion, sticking, and galling. So that is severe adhesive wear. Where material from one surface transfers to another, causing high wear rates. All these points comes under this compatibility. Next, crystal structure. So hardness and ductility. The crystal structure of a material determines its mechanical properties such as hardness, ductility, and toughness. Generally, hardened materials with certain crystal structures, example face-centered cubic metals FCC, may exhibit lower wear rates under specific conditions. The dislocation moment, the ease with which dislocations move within a crystal structure affects wear. For instance, body-centered cubic metals, which have fewer slip systems, can be more brittle and wear differently compared to FCC metals. It's a crystal structure. Next, phase transformation. Some materials undergo phase transformations under stress or temperature changes, altering their crystal structure and consequently their wear characteristics. For example, martinistic transformation in steels can increase hardness and wear resistance. Due to this phase transformation under stress or temperature changes, this type of wear resistance will be occurred. So next question, name any four experimental methods of wear measurement and explain any one of them. How to list out the four experimental methods and then how to explain any one experimental method. So here four experimental methods of wear measurements given. One is pin on disc test, ball on disc test, weight loss method, and surface profilometry. These four methods are used to wear measurement. But nowadays, frequently using this pin on disc test, whereas in research labs and academic labs. So explanation of pin on disc test. So pin on disc, the pin on disc test is a widely used method evaluate the wear resistance of materials. So in this test, a pin which can be made of the material under test or another material is pressed against a rotating disc under a specified load. So rotating disc here place. So this is this figure. In this the figure represents the pin on disc testing machine. So in this the pin is pressed against the rotating disc. Whenever this disc is rotates, so when the which job, which material is to be tested, so that is placed in an specimen boulder. So whenever this pin pressed against this disc, a rotating disc, so some wear will be occurred. Both can be measured to determine the wear resistance of the materials involved. So whatever load required, that load applied, and then distance you can adjust the radius, the distance, and then you can calculate the wear rate for different materials. So procedure here given. One is setup. The pin on disc operator consists of stationary pin and a rotating disc. The pin is mounted vertically and pressed against the horizontally rotating disc. So the load applied to the pin is controlled and can be varied. So load you can apply. The material selection, the pin and the disc are made of the materials to be tested. The pin is usually cylindrical or spherical shape, and the disc is flat and made from material with a known surface finish. So this is material selection, and setup is a procedure in a pin on disc. The testing conditions are, the test conditions such as load, speed, and duration are set. The durations, speed, and load are set according to the standard test protocols or specific experimental requirements. So as per testing manual, the running the test, the disc is rotated at the constant speed. The pin is pressed against the disc with a controlled load. The rotation of the disc causes relative motion between the contacting surfaces, leading to wear. So next, wear measurement. The wear can be measured in various ways. One is weight loss. The weight of the pin and disc is measured before and after the test. So the difference in weight indicates the amount of material lost due to wear. Wear volume. The volume of material worn away can be calculated based on the dimensions on the wear track on the disc or wear square on the pin. Next one is wear depth. The surface profilometry can be used to measure the depth of the wear track or scar, giving a direct measures of wear. So next, data analysis. The wear rate is typically expressed as volume loss for unit load and the sliding distance. So that is mm³ per Newton meter. This allows for comparison between material and testing conditions. The applications are, the pin on disc test is used to study adhesive wear, abrasive wear, and frictional properties of materials. It is applicable for testing metals, ceramics, polymers, and coatings. The test provides insights into the wear mechanisms and helps in the development of wear-resistant materials and lubricants. These are the applications of our pin and disc test. What are the advantages? The advantage of pin and disc test is simple and relatively inexpensive setup. Can be used for a wide range of materials. Provides direct measurement of wear and friction. The limitations are, may not accurately represent real world conditions due to the simplified geometry and controlled environment. The results can be influenced by factors such as humidity, temperature, and surface finish, which need to be carefully controlled. So these are the limitations. So sometimes the mission results influenced by these factors. Next question is, so what are the precautions to be taken keep adhesive wear magnitude lower? So one is material selection. So choose materials with low adhesive tendencies. Select materials that do not easily form strong adhesive bonds. For example, pairing dissimilar materials often reduces adhesion. Example, steel with brass. Use harder materials. Harder materials are generally more resistant to adhesive wear. Consider using materials with a high hardness like ceramics or hardened steel. So this is the precaution you can take to keep adhesive wear magnitude lower, the material selection and use of harder materials. And surface treatments and coatings. So apply surface coatings. Use coatings such as nitrates, carbides, or diamond-like carbon to reduce surface adhesion. Surface treatments. Techniques like carburizing, nitriding, or anodizing can enhance surface properties and reduce adhesive wear. So lubrication part. Use effective lubricants. Proper lubrication creates a film that separates the contact surfaces, reducing direct metal to metal contact. So the choose appropriate lubricants. Select lubricants with additives that can form protective boundary layers, such as anti-wear and extreme pressure additives. Next, surface roughness and finish. Optimize surface roughness. Ensure surfaces are neither too smooth nor too rough. A moderate surface roughness can reduce adhesive wear by minimizing the real contact area. And surface polishing surfaces to an optimal finish can help reduce high asperities that contribute to adhesion. Next, operating conditions. So operating conditions are one is control load. Minimize the load applied on the contacting surfaces to reduce the intensity of adhesive wear. Reducing sliding speed. Lower sliding speeds can reduce the energy level for adhesive junction formation and breakage. So avoid high temperatures. Keep operating temperatures within a range that prevents softening or chemical reactions that promote adhesion. These are the operating conditions. Contact geometry. So design for minimum contact area. So designing components with the minimal and controlled contact areas can reduce the likelihood of adhesion. Similarly, use rolling contact instead of sliding. So whenever possible, design systems to utilizing rolling contact, example ball bearings, instead of sliding contact to minimize adhesive wear. Next, environmental control. Environmental control means the maintain clean surfaces. Keep the contacting surfaces clean to avoid contamination that can exacerbate adhesive wear. The control humidity and corrosive environments. Avoid operating in environments that can lead to corrosion or oxidation, which can increase sorry the control humidity and corrosion environments. Avoid operating in environments that can lead to corrosion or oxidation, which can increase adhesive. The regular maintenance and inspection. Routine inspection. It inspects surfaces for signs of wear and address issues promptly. Maintenance schedules. Follow maintenance schedules to ensure that lubricants are replenished and worn parts are replaced before significant wear occurs. Next one is describe briefly about zero wear limit. So, what is this zero wear limit? It refers to a theoretical condition in tribology where the wear rate of a material or component is effectively zero. The theoretical condition in tribology where the wear rate of a material or component are zero. This implies that there is no observable material loss or degradation due to wear during the operation of the system. While achieving a true zero wear limit is practically impossible, the concept helps in understanding and striving for the ideal conditions where 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 is minimized to the greatest extent possible. So this is called as zero wear limit. The key points about zero wear limits are: one is definition, another one is practical considerations. The definition is zero wear limit is the point at which a material or component experiences no detectable wear. This means there is no loss of material or change in surface characteristics or water. Next, second case practical considerations in real world applications achieving zero wear impractical due to factors like surface roughness, contaminants, and operational stresses. However, minimizing wear as close to zero as possible is often the goal in engineering designs. Next, factors influencing wear rate. Several factors contribute to wear, including load, temperature, surface roughness, lubrication, and material properties. By optimizing these factors, the wear rate can be significantly reduced, approaching the zero wear limit. What is the importance of design? So, understanding the zero wear limit helps engineers and designers develop systems with very low wear rates. This involves using advanced materials, coatings, and lubricants to extend the life of components. So, these are the factors influencing the wear rate. Next, wear measurement. So, achieving zero wear limit often involves highly precise measurement techniques to detect even the smallest amounts of wear. The techniques such as surface profilometry and micromorphology analysis are used to monitor wear closely. So, whereas in these theoretical and practical goals, the concept of zero wear limit is used both as a theoretical benchmark for research and as a practical goal for high performance applications where the wear needs to be minimized as much as possible, such as in aerospace, precision machinery, and high value components. So these are the references I have taken. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.